Okay, hi everybody online, and with everybody watching the recording. Thank you for being here for the second installment of the string theory course we are teaching under the umbrella of Namgan University in the continuing education section. Thank you everybody for joining and for wanting so much to learn string theory. We really appreciate that. Okay, so now we will actually start with the second half of the lesson, the classical non-relativistic string. There was a short, well, actually, let me see. I'll review a little bit from last time, and then we'll start with the second part. So last time, we noticed the fact that one goal of string theory was to unify all the theories in physics somehow, and that it occurred because of the tensions between general relativity and quantum mechanics. So, because of that, string theory appeared, and we will see that in this course. The fact that the Standard Model, which is a very appreciated theory in particle physics, is actually coming out naturally from string theory. So we will see that a bit later in the course, towards the end of the course. And so this will actually indicate the fact that string theory has predictive power. There are naysayers still that say that, oh, well, string theory is nice and a lot of good math and things, but does it have any predictive power? And you can always answer to that question with a strong yes. And you can give at least this example, which you will learn in class, how standard model is coming out of string theory. And we will study a review paper and also a paper from 1985 of Candela, Horowitz, Streminger, and Witten, which builds on the heterotic string theory, superstring theory, the E8 times E8 one, and how from there it gets you into obtaining four, not three, families of particles. Of course, if they wanted to, they could have obtained three, but they wanted to go for four families. I mean, if they have chosen, if they chose a Calabi-Yau manifold differently, because the number of families you will see in the standard model and in string theory is related to the topology of the Calabi-Yau manifold, which we learned last time, is the compactified manifold, which sits at each point on the grid of the space-time. We learned last time also that space-time is not continuous, but it's very likely a grid, and that if we have this view, that's perfect. There are trans-Planckian modes, so beyond the grid, which has a side of Planck length. But as I said, there are trans-Planckian modes, but we stick with the view that actually space-time is a grid, and that what's in between the grid are some entropic families of particles, which are not matter, really. They're just ensembles of entities, let's say, of entities which populate the space. There's no space, but it's hard for us because we are space-time creatures. So it's hard to imagine something and ensembles of particles. I mean, they're not particles; they're entities that describe something that's non-spatial. So anyway, it really is a little weird. But we don't go there. If you are interested, you can read some papers about gravity as an entropic force by Verlind. And yeah, who's interested can email me separately, and I'll give you some refs about that aspect of things. But anyway, um, it's another thing is that gravity emerges naturally in string theory, and so in string theory and closed string theory will have a graviton present, and that is a sign of the emergence of quantum gravity from string theory. So you can say that string theory is a theory of quantum gravity. So anyway, also string theory will allow us to understand the Big Bang theory and whether is a Big Bang cosmology or not. So it has a lot of capabilities, string theory, not only to determine the standard model, it goes to Big Bang, it goes to this entropic um, um, entities from which the space-time occurs, and more. So it's a very hefty theory, quite developed at this point, but perhaps not yet developed enough. It still has to go further and explain many things, especially related to the standard model, which it currently cannot explain certain things. I mean, it derives the basic features of the standard model, but not some of the details. So we need more string theory to derive those details. So anyway, that's from last time, and now we will turn to just a second. Classical non-relativistic strings, and we go back to the rest of the theory after we finish that. I thought since the first part of the lesson deals with special relativity and quantum mechanics, that we gear into classical physics first, so classical non-relativistic strings, which are very important. Of course, strings are quantum and relativistic, the ones we employ to to derive, not to derive, to notice the presence of the graviton, for instance, and of the photon. So those theories are quantum and relativistic, and we'll get there while the class unfolds. We will get to that point later. But even if they look humble, classical, and non-relativistic, so not something we deal with, they actually have a lot of significance. And the reason for that is that the equation that describes the classical non-relativistic strings is later on, in certain circumstances and certain gauges, recovered for the relativistic strings. And then you quantize and you get the quantum relativistic strings. But as I said, this equation describes actually in a certain limit and in a certain gauge relativistic strings as well. So if we see it at work at the classical non-relativistic level, then we will understand better the relativistic string. And then when we quantize it, that's even better. And we will see that, in a sense, I mean, there's a lot of hype that string theory is something incredibly complicated. And like in string theory, there are dualities, and so something incredibly complicated is dual to something incredibly simple. you know. Um, I mean, in string theory, there are dualities like that. We will see T-duality at work. Where, you take a small radius theory, and that's dual to a large radius theory. So, and a weak coupling to a strong coupling. They are dual. So here also we can say that something that's incredibly complicated is actually dual to something incredibly simple, and that's string theory. It has these properties, these facets. Um, and why do I say that? Well, because it is very complicated. It has a lot of math. We don't go there in this class. We just keep it at the level of high school math and college math. Beginning college math, not something very complicated. So mostly high school math in order to understand these things, because Professor Zwiebach was nice enough to compile the essence of things for the bosonic string theory for us. And so he limited himself to that type of math. So he didn't go into complications. Um, so, but if you want to study, as I said last time as well, if you want to study string theory properly, you need a lot of math. A lot of math is necessary to study complicated, advanced PhD level math in order to study string theory properly as a professional. So, but here we are going to study, um, you know, bosonic string theory in a simplified version. So that we understand the concepts and not delve so much into math. We'll have a math-oriented lesson when we explain how we derive the standard model from string theory, because we need to understand the Candela's paper. But beyond of that, we stick to college math as well. Beginning, like first year. So what can I tell you? That's the complicated part. Why do I say it's incredibly simple and that it is dual to this incredibly complicated thing? Um, there is a statement in spirituality which says something like the big way is always incredibly simple. So that applies to string theory. So if you want to look at string theory, what do you think you see after you will pass through this class? Um, you will remain with this strong impression that what are strings? They are a bunch of quantized harmonic oscillators, actually. So that's string theory, something incredibly simple. That's what strings are, a bunch of quantized harmonic oscillators. So all that incredibly complicated math, backwards and forwards with homotopy, homology, cohomology, and first term class, and you name it, Witten index, Dirac index, Atiyah-Singer theorem, you name it in higher math, that is linked to string theory. Yeah, but what are they? They are a bunch of quantized harmonic oscillators. Something incredibly simple. That's what they are. So it's dual, something incredibly complicated, dual to something incredibly simple. That's string theory. So, okay, after this prologue into today's lesson, let's turn to the classical non-relativistic strings. Here, there's an introduction telling you about the first part of the lesson, which we will actually go over in the second part. But anyway, if there are any questions, I mean, you know. Okay, so everything is crystal clear so far. Wonderful. Okay, so let's take a look at the classical string. Um, so, as I said, the understanding relativistic strings and quantizing them requires a good handle of classical non-relativistic string treatment. So the only parameters that characterize strings are its mass, their mass, and the tension of the string. Um, they can also vibrate transversely and longitudinally. Um, mm, okay, so we will derive the equation of motions heuristically and also from the appropriate Lagrangian. Just like you do in classical mechanics for equations of motions. You have a Lagrangian, an action, you vary the action, and you end up with a Lagrange with the equations of motions. The equation of transverse oscillations of a stretched string, boundary initial condition, non-relativistic to study in this first part of the lesson. Um, okay, so the equation of the transverse oscillation, as I said, we will do a heuristic initially, and then we go to the Lagrangian, and we place our string. Let me actually take a look at the picture here. So we will assume the vibrations of the string are transverse. We will see this property is kept throughout the string theory course, and we will deal with transverse vibrations to the chord itself, to the string. So you will assume that there's a piece here of the string, um, and there are tensions here at the ends. It's a small piece of the string. It's not shown here. I don't think I have a picture of that. But in the Zwiebach book, and I encourage you to consult Professor Zwiebach's book occasionally to go beyond what we do in class, and to see he has many pictures. We can't use that many pictures in this class, and they are quite compelling. So let me see. I don't think I prepared. Well, we'll go there later. I have not prepared the whiteboard, but that's okay. I can generate it later. So anyway, you can imagine a string with boundaries and being kept fixed. Let's say that would be Dirichlet boundary conditions. At the ends. But anyway, you have this piece of the string. You have a tension here, tension here. This is x. This is x. I'm sorry. This is x. This is y. This is y plus dy, and this is dx. Okay. So we want to derive the equations of these transverse oscillations. And we'll do that strictly in a classical view. We will equal the force with mass times acceleration. That's Newton's second principle. So we will use that to derive the equation of the oscillations, which is, incidentally, I can tell you up front, the wave equation. That's what we are going to end up with. People who have taken differential equations classes can appreciate that actually the equation of vibrations of the transverse oscillation is actually the wave equation. So we will assume the oscillations are small, so dy to dx much less. Actually, if we take a look at this picture again, that this angle here, theta, is small. so the tangent is dy to dx, um, and so the sine of the angle is equals approximately the mm, tangent of that angle and equals the angle itself. We will need that to derive the equations of motion, which are, as I said, the wave equation. Um, yeah, I mean, anyway. So we placed our string. Let's follow the prescription here. We place our string with fixed ends at 0, 0, and a0 in the xy plane. So imagine an xy plane with 0, 0, a0. And T0 be the tension, and M0 is the mass per unit length. And the string will be a classical non-relativistic one, and its motion is pictured on in the following slide. Yeah, we saw that. The oscillations are small, so dy to dx much smaller than 1. At any point on the string, the length of the string changes little, and we assume the tension T0 is unchanged. So these are the assumptions we make. And then we go further, and we see that we want to project on the net vertical force. So we have the tension acting. We assume there is no gravity to act on the string. So the only force that actually acts on the string is its tension. So if we look um, a little bit further, let me see if we can. Yeah, we can actually see those equation 2. If we project on the vertical line, that's the vertical line of the T0, that would be the sine of this angle, which is sine here, which is actually the tangent is dy to dx. So T0 times sine, which is dy to dx, minus the same thing at the other end. We have to end here, this end and this end. The difference between the two, one at the force taken at x plus delta x, the other force at x, gives us this. Why do we get that? Well, it's the definition of the derivative. Um, so, well, I have to try to open a whiteboard. I'm sorry, I have not prepared it, so bear with me for a second. It's going to be an introduction. I should have prepared it. I thought I won't need it, but yeah. So, if there are any questions in the meantime, um, you can ask any questions you want related to this or anything in string theory, actually. To the whiteboard. Yeah, just second. Um, it loads very, very slowly. That's why I should have done it beforehand. Yeah. So all sorts of extraneous things here on the whiteboard when we start, which I have to get rid of. So, okay. Okay, so now we have a whiteboard. Okay, now you should be able to see my whiteboard. Okay, let me grab a pencil. Yeah, I just want you to understand how the wave equation is derived from heuristics. So you have the string, you have T0 here, and you have T0 at the other end, and this is dy, and this is dx. This is the angle theta. And this is the vertical force. And this is the vertical force as well here. And we have which is T0 at this end here. Dy to dx at x plus dx. Okay. So this is at point x. um, this is at point x plus dx. Ah, um, at dx. Okay. So basically this thing is the equivalent. If we divide this by dx, um, it's really the expression of a derivative. So it's this is really x plus dx um, minus f of dx. Of course, dx is small, so that's a limit. Dx goes to 0, which is actually f prime. And of course, t0 is a thing that gets derived, is dy to dx. So this is so roughly speaking, that's why we get what we get. So that's via this is the f vertical, and this is mass times acceleration to y to d length times dx is now if you of transverse waves, which is the inverse velocity, and that is the from heuristics, not from the Lagrangian. We'll do that with how the wave equation for the classical, not the equation of motion, physically in the waves on the string. And that's the equation. Okay, of course, you have to dig up and how to solve that and what kind of solutions that differential equation actually has. And like many, how should I say, well-posed problems in differential equations, you need initial conditions or boundary conditions to solve for the constants you incur when you solve the differential equation. And these are usual boundary conditions. There are other types of boundary conditions, Robin boundary conditions, and more that you can have on a differential equation. But in this course, we work only with Dirichlet boundary conditions or von Neumann boundary conditions, von Neumann or Dirichlet. These are the Dirichlet boundary conditions, so fixed points. Now, if we go back to the whiteboard for a second, just to exemplify just a second, let me go down here a little bit. So if you have the string like that, and the walls or some sticks or some walls here, and in between the walls, I mean, this is not one of those strings be thought D-branes, the DP branes. We have not introduced DP branes yet, but there are those hypersurfaces or surfaces that live in the 26 dimensional space, because I think we mentioned like last time that the bosonic string lives in a target space. That's what it's called, target space, in a target space of 26 dimensions. The superstrings live in 11, 10, or 12 dimensions. We will see a bit of work in 10 dimensions in this course. So it could be 26 dimensions or it could be 10 dimensions for us for superstrings. But the vast majority of this class deals with a bosonic string, which lives in 26 dimensions. And the reason for that, I remind you, is that to be anomaly free. And we will see that actually these 26 dimensions, we'll see in class how they occur from the fact that we impose the theory to be Lorentz invariant. So if we impose the condition of Lorentz invariance, then the bosonic string has to live in 26 dimensions. It's a condition that you will see how later in this course, how you impose Lorentz invariance and you end up with 26, a requirement of 26 dimensions for the space-time. So, anyway, you can imagine the string, the actual string. So it moves like that. And these are fixed boundary conditions. It means are fixed on the walls, which the walls could be in the quantized case, in the small string case. I mean, this theory is general for any string. A small and quantum, and so the strings, our strings, could have the ends end on a, I'll draw it here, oops, D branes. So there are extended surfaces like that. And the ends of the string could be on a D brane. I drew here D2 brane, two-dimensional brane. So that's a D2 brane. But of course, you could have anything from D0, actually D-1, D-1 to D25. The 26th dimension is time. So, and this to record spatial dimensions. So that's a DP brane or D2 brane, and you could have the strings ending on D2 branes here are fixed. The ends are fixed. Then those are Dirichlet boundary conditions. So that's Dirichlet. Boundary conditions. And the other way of looking at the problem, so those ends are fixed on the walls. If we have two sticks, so a D1 brane in one dimension, so D1, a D1 brane, so this line, like that. And the ends of the string are free to move on D1 up and down on the D1 branes, on the two D1 branes like that. And these are von Neumann boundary conditions. We'll work with these. So these are fixed. These are the ends move freely. So von Neumann. Man boundary conditions. Okay. Uh, so that's what I pretty much wanted to show you. How are the von Neumann boundary conditions and the Dirichlet boundary conditions? And now we go back to the slides and we try in a couple of minutes to do as much as we can, and then we come back after 10 minutes to finish as much as we can. You have the slides. If we don't finish the slides, you finish the slides yourselves. I can't go as like a machine to cover everything fast and quick and all good, and to explain and everything very fast. So I go at my pace. And so we may not finish the slides. However, you have the slides, and you can review them, what's left yourselves, and then you can ask me questions in private or during the lesson. I didn't understand that. Please explain. It's a lot of material, so it's hard to cover everything. We do our best. Okay, so that's the boundary and initial conditions, the Dirichlet boundary conditions and the von Neumann boundary conditions. And now we go to the solution of the transverse wave equation, which is that equation with partial derivatives. And we know from the theory of differential equations that to solve the equation of the transverse waves, we have a superposition of advanced waves and retarded waves. So there are arbitrary functions of a single variable, which is a superposition of two waves, as I said. And the initial conditions are these. And so we can solve the equation for H plus and H minus knowing these boundary conditions. You have to know a little bit about differential equations and their solutions. But in any case, that equation has this type of sign. The sign of omega, the frequency of oscillations. So y of t and x is something like that, is the solution of it's a superposition of actually of sine of cosine, which if it's sine or cosine is determined by the boundary conditions. So for Dirichlet boundary conditions, you have this one. For Neumann boundary conditions, you have a cosine, and omega, the frequency of oscillation, is the same in both cases. So in any case, the wave equation, what you have to remember, has a solution of superposition of sine and cosine, and you solve that with the boundary conditions and the initial conditions. You can give the solution, which is that superposition of H plus and H minus, advanced and retarded, which gives this sign in the end. I mean, advanced, an exponential, and the other one an exponential, and it forms a sine or a cosine depending on the boundary conditions. So we don't have time to go over, differential equations. It's a theory. It's too much for this class. So you have to know certain things. If you are unfamiliar, you look it up on the Wikipedia, and you see why these things happen like that. They must have some, or the AI teaches you quickly how to solve the wave equation. Okay, I think we will stop here so that we start we have a little bit left here, the non-relativistic string Lagrangian, how to derive the equations of motion, so the wave equation from a Lagrangian. We'll see that after the break. So we'll start 10 minutes from this point on. Yeah, you have to let me know if I don't share the right thing. Adrian, you have to pay attention and let me know if I did not share. I went over the slides and the slides were not on. You have to let me know if I do that. So
Okay.
I explained about 5 minutes of work, and the slides were not on. You have to let me know about that if that happens again. Okay. Okay. So 10 minutes break. Okay, we are back. I hope everybody's back. So, just a second. Adrian, if you want to take a screen share for the ones that are present, because there was an extra person. There were 10 people at some point. So, you know.
Yeah, no worries. I took a screenshot.
Okay, very good. Yeah, we don't want people to be present and be not counted in, you know. Okay. Um, so so we'll go back to our lesson. I'll go over this thing again. It's just 1 minute now, because I was not sharing the screen. So basically, oops. As I was saying, the equation the solution to the equation is a superposition of advanced and retarded waves. And really and truly, it's a superposition of sine and cosines, the solution to the wave equation. And it can be represented like that, like in equation 10. That's the solution. And if you have Dirichlet boundary condition, then you have a solution like this. With an omega, which is the same for Dirichlet or for Neumann. And this is like that. So it's really a superposition of sine and cosines. And depending what kind of boundary conditions you put, that's what you end up with a cosine or a sine. Um, and as I was saying, you should kindly refer to Wikipedia on how they solve, or AI, artificial intelligence, how they solve the wave equation. Adrian will show you a few things during the seminar, and so during the discussion section, and you will be able to appreciate the details of solving a differential equation with boundary conditions and things. So you'll have the opportunity to see these things at work. So this is the most important part of this lesson. Of course, Adrian will help us out. Understand more. You understood as much as you could. You'll understand some more when he does the problem for you. And we go ahead and we work with non-relativistic Lagrangians. So the same equation can be derived from Lagrangian considerations. So how do we construct? This is the potential energy in the Lagrangian, and it's constructed from here. You do a Taylor expansion of this one, and you end up with this one. I don't have so much time now. I have to speed up a little bit because, well, I have to cover as much as I can. So, because you already know how to derive the wave equation, now it's just an additional way of doing it. So you reach the wave equation, you solve it with the solution. You'll see some more with Adrian. So you have an idea about the classical relativistic, non-relativistic string. And that's important to keep that clear, that the wave equation is the equation of motion for the string, the classical string. And as I emphasized, it's also in certain gauges and certain conditions, also the equation of motion for the relativistic string, which is the basis for what we do to quantize the relativistic string later on to get what we want, those bunches of oscillators that I was telling you about, which they oscillate and give out the graviton, the photon, and if the string is superstring, the electrons, quarks, and so forth. So that's how matter appears, so that you make that's extra clear for you from vibrations of strings. So the strings vibrate in a certain way. Also, they vibrate into a Calabi-Yau and manifold, which is compactified and small. And depending on the shape of the Calabi-Yau, you end up with such and such electrons, muons, tauns, and such quarks, and such Higgs bosons, and everything else. So, that's how things go. They come from strings. The kinetic energy term is, of course, a velocity times mass. And so if you put these things together, also from heuristics, the potential term is from heuristics. This is the non-relativistic classical string Lagrangian. This is how it looks like. And now you have to take a variation of the action. This is something you learn in first year or second year, perhaps first year college class in classical mechanics, in analytical mechanics, how to get the equations of motion. So you learn these things in that course. If you're not familiar, again, Wikipedia. So you take the variation of this equation. So it's 1/2 with this 2 goes. So it's dy dt, variation of dy dt. And here, again, the same way, a variation of delta y dx. And here, you force a total derivative here. So you do it here, like that here, minus the term in dy dt, which becomes d2y dt. Same thing here, you force a total derivative, and you have that there. Then you group these things together, and you integrate here over over dy, and just a second, over dx, I meant. Yeah. Yeah, it's a dx here. So integrate over dx. Actually, you integrate over dt here because the total derivative is on dt. So you end up with this term from t equals to t initial to t final. And here, again, the same thing. You integrate over dx from 0 to a, 0a. And you end up with this equation. These terms will cancel. So the equations of motion, in order for you put this one equals to 0, so this one has to be equal to 0. And the reason those terms cancel are like that. The first cancel the first term because you have this one equals to 0, and the second term, it's either because you have Dirichlet boundary conditions, or you have for Neumann boundary conditions, the second term cancels as well. So you have the only term left is this one, and those are the equations of motion. And it's what we derived before. So if you look carefully at this term and you make it equal to 0, you retrieve the wave equation. So that's from Lagrangian considerations. And now something that one of your colleagues wondered, the fact that the string momentum is not conserved with Dirichlet boundary conditions, and that's true. The momentum of the string. However, if you have dp branes, as I explained earlier, d0, d1, or d minus 1, which are the instantons. So instantons, particle is d0, d1 is one string, d2 is a plane or something two-dimensional, and so forth. So DP branes, you attach the strings to the DP branes, and then the momentum of DP branes with the string combined conserves. So is conserved. So it will be conserved in the context with the DP branes, really and truly. Um, and that we'll learn about these things later. This is just to bring to your attention the fact that the string momentum is not conserved by itself with the boundary conditions. But if you add the DP branes, then together it is a conservation, and that applies, of course, only to open-ended strings. So we know that string theory operates with strings which are open, so with two ends which can be attached to DP brane, or closed string theory, where the string is sort of a circle or topologically equivalent to a circle. And so we will learn about these things later, just to make sure you get to know these things at this point. Okay, so now we'll go back to the first part of the lesson. If there are any questions. Okay, so preparing the grounds to quantize the relativistic string, which means we'll learn a little bit of quantum mechanics and a little bit of special relativity. I mean, we don't actually, we prepare the grounds, but we don't get there yet because we have some stuff to learn until we get there. Okay, so short review of special relativity. Okay, the speed of light in vacuum is, everybody knows, 3 times 10 to the 8 meters per second, I hope. This is one of those typos, which these slides are full of typos, I must tell you that. And I think I told you from the very beginning I was not going to correct the slides because that's your job, to catch all the mistakes, which are typos. Basically, I don't think I introduced intentional mistakes in the slides, but it's full of typos. And so your job is to catch them, and to bring it, not necessarily to my attention. You can bring it to my attention as well during class if you want to, that's okay. But you bring it to your own attention, and you learn more. It keeps you on your tiptoes when you know that there are mistakes, which you have to catch. Okay, the relativistic interval is this fellow here, like that. There's a minus sign in front of the time. This is time. These are the spatial coordinates. So I assume you have some background in special relativity and you have some background in quantum mechanics. I mean, not a lot, but some background, so that you understand, for instance, the relativistic interval. So these are the events. I'm not sure I have a picture here, but I probably do, of the light cone. Let me see, so that we learn these things faster. We have something, but not what I want. Just a second. Let me backtrack a little bit. So just to remind you a little bit, I'll go to the whiteboard for a minute. Yeah, some issues with whiteboard. Okay. If, if I can retrieve the pencil, that would be fantastic. is at my end here. Everything is okay. Um, have a pencil now. Okay, so if you place yourself, let me enlarge the zoom here. Of course, this is the Minkowski light cone, and in higher dimensions, it's really a cone like that. Or x0, how it's notated in the class notes. That's t, interchangeably t and x0. X0 is time. And so you have the light cone here. And what's inside the light cone, it's causal and can be reached by particles, line worlds. They have to stay within the light cone because their speeds are smaller. This is c x0, and actually minus, and this is c x0. And so everything has to stay within the light cone because their speeds are less than the speeds so of light. So all the physics that's interesting, well, not to say that the other physics outside the light cone is not interesting, but from the inside of the light, if you want, people familiar with black holes, the light null arrays, because these are called the null rays of the Minkowski cone, are sort of horizons for the particles inside the cone. You can't go beyond. Okay, so that's just very little, but I assume you know these things. It's just a review. Um, Let me go back to the slides. I'll share this. Okay. And so eta mu nu is a Minkowski metric. Let me go back to the whiteboard for a minute. Um, um, the metrics, you should know a few things from first year college student class about metrics. Um, so eta mu nu is really the Minkowski metric in matrix format, because all these tensors with two indices are actually matrices. So it's minus 1, 1, 1, 1, and a bunch of zeros here and a bunch of zeros here, and that's the diagonal of the matrix. And that's the Minkowski matrix. We'll encounter a little bit of other metrics when we study in this class black holes. So we'll see there all sorts of metrics of black holes. But this is a flat metric. It is the metric in the space time we live in around here on planet Earth. So it could be Euclidean, which means it's a plus here, not a minus. But it could be Minkowski as well. That with a weak rotation, you can go from Minkowski to the Euclidean space. So So that's okay. Okay, let me go back to the lesson. Okay, and of course, if you have that minus sign, you raise indices. Adrian taught you a little bit about these things last time in the seminar. If you need to review those indices down, indices up, if you need to review those things, Wikipedia or Adrian's notes and recording. Okay, the relativistic energy and momentum and proper time. Energy and momentum is like that. Momentum for momentum, that's in this is up and in this is down. They usually differ by a minus sign because in the Minkowski matrix, which raises and lowers indices. I mean, basically, what can I tell you? So if you have um, a mu like that, the Minkowski metric raises um, um, or lowers indices like that. So if you have something with upper indices, you go to down indices with a Minkowski metric like that. And that's a new here. So eta mu nu applied to this one gets you here. So you have lowered the index and you can go up with the index. So the Minkowski metric, you know that from first year algebra. Oh, I'm sorry, I have to put it up. Yeah. From first year algebra. You know these things, how to lower and how to raise indices. So that's why you get that minus sign because you
Teacher,
have basically
the whiteboard is not
yeah,
visible.
yeah, I have not shared. Okay, sorry. Okay. Okay. Yeah. So anyway, um, you lower and you raise indices like that. And you have the Minkowski metric, which I hope that was visible up here. So this is lowering indices and raising indices like that with the Minkowski metric. Is that okay? Anyway. Yeah, we assume you know these things actually. So just a review. Um, okay. Um, okay, so there exists another Lorentz invariant the proper time. And the relativistic interval is written like that, where beta is V over C. And so it can be written like that, the relativistic interval. Absolutely. Um, and now the two reference frame related by a boost along the
Uh,
OX. Yeah,
Teacher,
I have
the
not
slides.
shared. I have not shared the slides. Yeah. Okay. Sorry. Thanks. So we go back here, the relativistic interval, the proper time, which you know the dilation of time. So you take the proper time, and you dilate it with square root of 1 minus beta squared. So going from one reference frame to another. So two reference frames related by a boost, which goes like a VT like that. Um, then the Lorentz transformations for that are given by these relations here, 1 through 11. I think Adrian showed you these things last time in the seminar, the discussion section. So it's just for you to take a quick look like that at these things, and remind yourself about Lorentz transformations. More on Lorentz transformations. Well, they're really, in the general case, matrices L mu nu like that. So x prime is L mu nu times x nu. So that's in the first system of reference. That's in the second system of reference, the x's. And the relativistic interval obeys this relation. So you go like that. And you get this relation on the Lorentz matrix with the Minkowski metric like that. So transpose this T means transposition of matrices, and the Poincare group, which is an extension of the Lorentz group, has 10 generators, 4 for translations. The Lorentz group is 3 rotations and 3 boosts. So that's the Lorentz group, and the Poincare has added translations. We work in 4-dimensional space-time for now. That's obvious. So we study special relativity in a 4-dimensional space-time, and we derive these nice relations. There's going to be some homework. So again, the policy with the homework is like that. It's not going to be graded unless you want to share your work with Adrian, which is fine with him as far as I understood. So it's fine with that. But you try to do your homework in the privacy of your own home, in your own office. You do the exercises, and next time, Adrian will actually do a discussion section on this homework of this class. So this class has some homework assigned, and next time he will go over the entire homework in section in class 2, which is this one. So you'll have the solutions. But try, hard yourself to do these exercises yourself. It's a good practice to see how to do them. If you cannot do them, well, Adrian will show you how to do them next time, right? Right. Okay. Now we go to light cone coordinates. These are not just fancy things. These are coordinates in which we will actually do the entire quantization and work with a relativistic string and so forth. So Professor Zwiebach works in light cone coordinates. Could be other books like Polchinski. They don't necessarily work in light cone, but a lot of properties of strings and the properties of the theory are visible in the light cone coordinates. So it's really and truly a very good tool to work with light cone coordinates. And you will see the validity and the viability of these coordinates later on, like when we reach the spectrum of this closed and open strings, and we compare the Klein-Gordon equation of a scalar to Schrodinger equation and so forth. We'll see very interesting properties. So all these things become visible in the light cone coordinates. So that's why he prefers those that are very didactical. And they show you immediately the properties that are visible with a naked eye. So Light cone coordinates are defined like this: x plus and x minus, and x2 and x3 remain the same. So the light cone coordinates for 4 dimensions is x plus, x minus, x2, x3. Of course, if we work in 26 dimensions, you have to imagine there's x4 dot 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 until x 25, x24 actually, because there are two here and 24 more. That makes a total of 26. So it's 24 plus two more. That's light cone coordinates for a 26 dimensional space time. Right, right. Very good. Okay. Okay, so the light cone coordinates. Let me see if I can enlarge this a little bit. Um, I don't want to go the PDF. Hmm. I think now you have better visibility if I zoomed in a little bit. Is that better like that? I think you should be able to see the little scribblings here. So anyway, this is x minus, this is x plus, and here are the particle lines like that. You have a cone again, with x plus equals 0, x minus equals 0 like that. Because this is the rotated, if you want, system of reference. That's x0, x1, and this is x plus, x minus. The light cone metric, you go from Minkowski to this one, and n plus minus n minus plus eta, plus minus eta minus plus is -1, eta plus plus eta minus minus is 0, and eta to 2, eta 3, 3 is 1. So that's why it looks like this. It does not have a plus plus and minus minus. Those are zeros. Okay. And now let's consider a particle moving in the x1 direction with beta and the initial conditions like that. So the equations of motions are basically this one. Remember, x0 is time. So x1 is beta x0, and there's motion only in the direction x1. And what are the equations of motion in the light cone coordinates? They're like that. I think Adrian went over these things with you during the seminar, so I'm not going to insist last time. The light cone velocity is dx1. So if you take the derivative of this one and the derivative, I mean differential actually, to make it dx1 to dx plus 1. Obviously, this is dt simplifies. So you're left with 1 minus beta over 1 plus beta. That's a little exercise. I think Adrian did it anyway. And the light cone diagram here. Okay. And line 1, this line is beta approximately 1. The light cone velocity is 0 for this one. Beta approximately 1 for 2, and 3 slow particles, because everything here is in light cone velocities. Like if you look at the graph, this is x plus, and this is x minus. The new axis instead of x0 and x1 in light cone rotated like that, and what they actually mean in terms of velocities. um, and line 4 is a negative beta. The light cone speed increases, and line 5 beta is -1. Obviously, this is beta +1. It's like Minkowski cone, only in the light cone coordinates. Um, and line 2, 3, and 4 are inside the um, light cone in light cone coordinates. So light cone in light cone coordinates. Okay. And here for beta is -1, the light cone speed is infinite. Um, so apparently that's a contradiction, but with special relativity. But they say here, note that there is no contradiction between the fact that in special relativity the speed of light is constant, and the results for line 1 and 5. The light cone velocity is 0, and here is infinite. It is noteworthy that there is no Lorentz transformation that connects the light cone coordinates, these one, and the regular coordinates. So, you expect the Minkowski light cone to hold and special relativity to hold in this context, that you have a Lorentz transformation from one system of reference to the other. There is no Lorentz transformation connecting x0, x1 to x plus, x minus. So those are special coordinates which are not necessarily linked to the rest of the universe, if you want, in terms of Lorentz transformations. So they are by themselves like that, and they are heavily used in this class because of the properties the equations have in this light cone. But you cannot Lorentz transform from the light cone coordinates to the Minkowski coordinates. So that's an important property here to remember. Okay, now light cone energy and momentum. Of course, the P plus and P minus, plus up, minus down, up and down, like that. They're related this way through with a metric which is not the Minkowski metric. It's the lowering indices is now with a light cone metric. So plus and minus metric lowers and raises the indices. Um, and so that's the scalar product, like that, for light cone coordinates. And consequently, minus P plus would be the energy in light cone. Um, okay. The extra dimensions do not change too much the structure of Lorentz transformation, but in 5 dimensions, the number of boosts become 4 and the number of rotations 6. To scale back to 4 dimensions, we just make the fifth coordinate null. The same properties of Lorentz transformation hold in higher dimensions, just like in 4. So this relation holds in higher dimensions, like in our case with the 26 dimensions. I mean, they considered here 5 dimensions, but we actually work in 26 in our class in the bosonic string theory. It's because all these things are going to appear um, during various stages of this course. So it's good to have a good foundation. So try to insist to understand, especially with Adrian's seminar, the first one, try to understand Lorentz transformations and light cone coordinates, because we will use them a lot later on. Okay, compact extra dimension. An infinite light can be compactified into a circle by making the following identifications. Okay, so this is how you compactify a line. You roll it like that around a circle. and you get the torus. I mean, he explained to you these things last time. I'll go over these things again. So you compactify a torus, the x and the y over the radius r. So it's basically something he showed, and I'm not going to insist on that because it's in the previous seminar. So an orbifold, he went over these things also. An orbifold is a set with identifications that contain fixed points, such as r/z2, which is r with the identification x minus x. And x0 is the fixed point of the orbifold. If you had an interval, then you'd have a fixed point of the interval as well, let's say -1 and 1. You have seen circle compactifications before. Okay, moreover, one can imagine compactifications of 10-dimensional superstring theories on a T6 torus. A T6 torus is basically three tori of 2T2 tori. So three regular torus, when you have the square, you identify the sides of the square. Like that, you get a cylinder. Then you identify the circles of the cylinder and you get a torus. Three tori like these form a T6 torus. So you don't need to be scared about T6. It's really three tori like that. And you compactify on a torus, on a T6 torus, from 10 dimensions down to 4 if you don't want to use Calabi-Yau. So there are legitimate string theory compactifications on a T6 torus from 10 dimensions down to 4. And of course, Calabi-Yaus are something else, are more complicated. We'll go over Calabi-Yaus later on in this class. But some more homework, I think Adrian already did for you, problems 2.2 and 2.4. These pages are in Zwiebach first edition textbook. Some of you may have the second edition. I work with the first edition. And so that's why 2.2, 2.4, and 2.6 are on pages 36 to 37 in Zwiebach first edition. Anyway, he did 2.2 and 2.4. He'll just do 2.6 next time. But take your time to review 2.2 and 2.4 done by him, and try to work 2.6 on your own. Okay, now we are done with the review of special relativity. We went fast, but again, we assumed you know these things. So now a bit of quantum mechanics. Any questions from special relativity or any other part of this class? Okay. We are all good? Okay, so one-dimensional square well potential of infinite height. We have a time-independent Schrödinger equation, which is this one. Of course, we again assume you know Schrödinger equation. We are not going to explain it, derive it, or anything else. And the potential is that of a square well. It's 0 between 0 and a, and infinity outside that interval. So you have to imagine like a segment with infinite walls. So the particle, classically at least, has to stay within that potential, within those walls. Okay, so then we have to solve this equation inside 0 and a. In that interval, we have this equation, which is again a differential equation which we know how to solve. It's the wave equation with consistent boundary conditions are like that. So the boundary conditions are the fact that you have the at 0 and a you have the wave function is 0. Those are the consistent boundary conditions, and you get the solution for this equation. Um, and the quantized energy levels are these. Um, and the square well with an extra dimension. Now we assume that we don't work only in 4 dimensions, but we include dimension y. Actually, here the problem was one-dimensional, so we go to 2 dimension. We include the y dimension. Only this time we say it's compactified, so it's curled up into a small circle of radius r, which means this identification. There should be an equivalent sign here, another typo. So the particle now moves on a cylinder of length a and circumference 2 pi r. So the potential Vxy is y independent as and is the same as in the regular case. Does not, the potential doesn't change. So the equation now looks the same way. The potential is 0 between 0 and a, and there is no dependence on y of the potential, so that's always 0 in the y direction. So we have this equation now, a two-dimensional differential equation. Now we know how to solve this one. This looks like a, not exactly, but sort of a non-homogeneous wave equation. So sort of. So we separate the variables. How we solve this differential equation? We separate the variables like that, and we integrate. We take this equation equals to something, and this equation equals to something, to a constant. So then we know how to integrate these two separately. This one equals a constant and this one equals a constant. And so the solution is this one. And with the boundary conditions, you have, because you separated psi and phi, there's a typo here, of course, that's a phi of y. So you have phi like that and psi like that. And we are very close to finishing, so I finished the slides, which is good. So the solution of phi is like that, a combination of sine and cosine with energy eigenvalues like that. So these energies correspond to doubly degenerate states when L is different than 0. Right. Because the solution contains two linearly independent solutions, so the spectrum has changed now to 2 dimensions. Now you have two quantum numbers. You have K quantum number and L quantum number. However, if R is much smaller than A, then this one can be ignored, and we get practically the same spectrum in A dominant. So one can probably exist. I mean, you don't really see the curved dimension. That's the point he's trying to make. That this term is curled up, and it's only visible at really high energies. Otherwise, you don't see it. So if L is really, really large, that compensates the fact that R is really, really small. So you don't see the fact that you have a curled up dimension in the square well unless you probe it at really high energies. So that's why we could have so many curled up dimensions around here, and we won't see it at regular energies. So that's another point for the curled up dimensions, why you don't see it. It's from quantum mechanics, from the square. Well, it could be a more complicated problem than that, but it gives you the idea that the small curled up dimensions don't show up in the spectrum. You don't see them. They're there, but you don't notice them because it's as if they're not here, practically. um, and the winding modes. So if you have a circle like that, we'll see winding modes later in the course. For a string, the situation is different, since new energy levels can appear when the string wraps around the extra dimensional, which are the so-called winding modes. The winding modes do not have an analog in the quantum mechanics of a point particle, and they actually can occur even if r is larger than the length of the string, or only somewhat smaller. And Professor Zwiebach is known in research for many things, but also for developing double field theory. Okay, so that ends our lesson here. We'll go on a break again. Um, so let me stop sharing here. The recording will stay, and Adrian will come back. And just a second. Um, he will come back, and he will deliver the discussion section. So stay tuned. I'll see you in 10 minutes from now. Okay. Have a good one. Thank you for being here present. Thank you very much. See you.
We will start the seminar in 1 minute. Okay. Hello everybody. I'm very happy to see you all back. Uh, Today we will move on with the subject of non-relativistic strings, and we will see a practical example of the things we talked about so far in today's lecture. Um, Teacher, is it okay? I can't share the screen. Could you help me with the share screen?
Yeah, sure. Just a second. Um, is it okay now? Can
Yes,
you
thank you.
share? Okay.
Okay, great. So as I said, today we will work on a example of a problem with non-relativistic string with some analytic mechanics. For those who are not familiar with the subject, I will read the problem and I will try to unbox everything that is said by parts, so everything is crystal clear to everybody. Okay. Today we will work on just one problem. We will start with the generic solution, then we will work with the boundary conditions, the initial conditions, but also the domain of the variables to come a, uh, with a solution to the problem, but also to apply the form of the function to find some nice results. Okay, so to start off with the first part, a string with tension T0, mass density mu0, and wave velocity v0, which is square root of T0 divided by mu0, is stretched from xy, which is 0, 0. Let's note this T0, mu0, which results that we know v0. Okay, and the string starts from xy, which is 0, 0, and ends up at xy a0. So the length of the string is a. It's just a normal string from the point 0, 0 to point a0. Okay, good. The string endpoints are fixed, which will come very handy in a second. And the string can vibrate in the y direction. So the string does not vibrate in other directions. It's very important, even though it seems obvious. But if you consider some more general case, which will not be as simple as this one, the points might go diagonally or in some weird directions. So fixing it, moving only on the y-axis simplifies it very good to get just the wave equation. Okay, so at the first point, we want to get from the general form of the solution y of tx being h plus function of x plus v0t plus h minus x minus v0t. And we want to find the relation between h plus and h minus, being h plus is equal to, wait one moment, h plus of u is equal to minus h minus u, and h plus is also equal to h plus u plus 2a. All of this from the initial conditions that the endpoints are fixed. These initial boundary, not initial conditions, the boundary conditions are named Dirichlet. So when the points are fixed here, they can't move at all. They are Dirichlet conditions. That means that y of 0, oh no, not 0, uh, t0 is equal to y of t a and is equal to 0. This is the Dirichlet boundary condition. Okay. There is another condition named the von Neumann condition, boundary condition, where the points are not fixed, but the speed cannot go, the derivative of the ends are 0, not the function itself. Okay, great. So by using this relation right here, we should derive these ones right here. Pretty simple for the first point. So to do this, we just take the first part of this condition. That is y of t0 is equal to 0. So we just replace x being equal to 0 in the general solution. That means y of t0 is equal to h plus of v0t plus h minus of minus v0t is equal to 0. Okay, so to get a relation out of this, of course, we move something on the right side. So h plus of v0t is equal to minus h minus v0t, okay? And we can get a dummy variable here, the v0t. We can just note it as any other variable. It just is change of variables for our own sake to be more simple. Okay, so we get h plus of u is equal to minus h minus of minus u. This is exactly the first relation we wanted to find here. So, okay, pretty simple so far. Let's check the second one. The second one comes from the second end that y of ta is equal to 0. That means that y of ta is equal to h plus of a plus v0t plus h minus a minus v0t and is equal to 0. Okay, now we do the same thing we did earlier by separating the parts. H plus a plus v0t is equal to minus h minus a minus v0t. Okay, great. Let me copy this. So we have, okay. Okay, great. Now Let's continue. So we have a very close form to the one that we found earlier with the minus h minus of minus u. So to get something similar and put it in use here, we could just say, okay, this part, let it be equal to minus u. So minus u is equal to a minus v0 t. So u will be v0 t minus a. But this term doesn't really appear anywhere in our condition here. So to get something that we know, we just add another 2a. So we get u plus 2a is equal to v0 t plus a, which is the term of h plus. So substituting everything into place, we get h plus is u plus 2a, which is equal to minus h minus of minus u. But we know that minus h minus of minus u is h plus. So we just say it's equal to h plus of u. So h plus is a periodic function. That's another hint that we work with periodic functions like sine or cosine. It appears naturally when working with such boundary conditions. Okay, any questions so far? Okay, I'm glad everything is clear. One moment. Good. Now, let's um, let's add more information to this because just knowing the boundary conditions doesn't really help us to get a explicit form of y. Like we have some properties for the h functions, h minus and h plus, but we can't really do anything with them if we don't know something specific. So for this, we will move to the second point in this problem. Now consider an initial value problem for this string. So we know something from the moment 0. At t equals to 0, the transverse displacement is identically 0, which means y of 0x is equal to 0. So let's write it down. Is equal to 0. Okay. And also the velocity is initially at 0x is equal to v0 x over a multiplied by 1 minus x over a. Okay, where a or where x is on the string. Okay, sorry. Good. Now we should, after getting these initial values, to get a form for h plus and inevitably for h minus also, because they are tied together. So to do this, let's first write the first condition here, that y of 0x is equal to 0. That means that by replacing t with 0, we get y of 0x is equal to h plus of x plus h minus of x, which will be equal to 0, of course. This means that h minus of x is equal to minus h plus of x. Even more conditions for between h minus and h plus. Okay, this wasn't very helpful, but we can get a very explicit form for h from the uh, initial velocity. So by deriving uh, the general solution, we get v0 h prime plus of x plus v0t plus, oh, no, sorry, minus h prime minus x minus v0t. Okay, so replacing t with 0, we get, okay, okay, good. Good. Now we got to this part, but we also know that h minus of x is equal to minus h plus of x, and their derivative would also uh, fit this condition. So from this relation here, it also means that minus h derived minus h prime. Wait, no, minus of x is equal to h plus prime of x. Okay, so but if we replace this in this relation, we get 2v0 h prime of h plus yeah uh, h plus derived in term of x. Okay, good. Now we have the general solution for in the when t is equal to 0, and we make it equal to this initial function that we know. So 2v0 h derived plus x is equal to v0 x over a multiplied by 1 minus x over a. Yeah, okay. And by moving everything in on the other side, we get h plus prime of x is equal to x over 2a multiplied by 1 minus xa. Okay, and now, now really, this is not really correct. We should use here the dummy variable because we will need to find a general solution, not in terms of x, it will be the general function, not because then it will be not clear how we just integrate in terms of x, or why not integrate also in terms of t or whatever. It is a general function, it's in terms of u. So this is more correctly put here, u, u, u. So there is uh, no confusion. Okay, so now all we have to do is to integrate this relation here. So we get h plus of u is equal to u squared over 4a minus u a third power over 6a squared plus c. Now we know that y is equal to h plus x plus v0t using the uh, property here. We get minus h plus x minus no v0t minus x. Okay, so if we replace all of this in the relation, we get a plus c here and a minus c here. So these ones cancel out. So we don't really have to keep track on the constant here. So it's just this function right here. Now, there is another issue that we didn't speak about, that we also have to keep the property that h plus u of u is equal to minus h minus of minus u, which will be h plus of minus u. And in this case right here, the function does not do that. We have the u at the power 3, which does not is not an even function. So to do this, we add here, so it fixes the problem here. We add a moduli minus moduli of u at power 3 over 6a squared. And now this function right here respects the conditions that we put so far. So this is the final form of the h function for the solution. We will see in the next part uh, how we integrate this with the domain. Okay, so any questions at this part? Okay, good. I'm glad everything is okay. Now, finally, after imposing all of these conditions, we would like to also impose a domain in which all of this is happening. So we should calculate y of tx for x and v0t in the domain D, defined by the two conditions. So this is point C. Have the domain which is equal to x v0t 0 less or equal of x plus minus v0t less than a. Okay, so we have to get solution of y from this domain. So to do this, it's not such a hard part. We write the conditions explicitly. 0 less or equal than x minus v0 t less than a, and also 0 less than or equal than x plus v0 t less than a. Okay, that means that x minus v0 wait x plus v0 t is in the 0a domain, and x minus v0 t is in the minus a0 domain. Okay, so by using also the property that h plus of u is equal to h plus of minus u, it means that we can flip here the sign. So v0t one moment. Oh no, no, I'm overcomplicating stuff. Sorry. No, it's that was all. No, we just define it this way, so it's on the entire interval. I had to make sure everything is all right because I was thinking I was missing something, but I was actually adding stuff. Okay, so After this, we just put in the functions of h plus. So y of dx is equal to bracket x plus v0t squared over 4a minus x plus v0t at the third power 6a squared. Here we don't need the moduli because it's positive. It's in the positive domain here. Okay. Minus x minus v0 t squared over 4a minus minus v0 t to the power 3 over 6a squared. Okay, great. Now, this is an okay result. This is correct, but we should also simplify it a bit because it's very it will be very hard to work with in the next point. So we remember that, actually, let's first group them together so it's more visible what I'm trying to show. X plus V0 t squared minus x minus V0 t squared over 4a minus x plus V0 t to the third power minus x minus v0 t to the third power over 6a squared. Okay. And now we use the relations for a squared minus b squared is equal to, in this case, a is x plus v0 t and b is equal to x minus v0 t. We get a minus b and a plus b. And of course, we get 4x for v0 t, but also for a to the third power minus b to the b cubed, yeah, is equal to a minus b, a squared plus ab plus b2 to the b squared, yeah, which will be equal to, I will not go into all the calculations, it's just replacing everything there. 2v0 t 3x squared plus v0 squared t squared. Okay. So replacing everything in there, we get y tx is equal to 4x v0 t over 4a minus 2v0 t 3x squared plus v0 squared t squared over 6a squared, which is x v0 t over a minus this cancels out, v0 tx squared over a squared a squared, then 3, oh no, not 3, v0 t all to the power of 3 over 3a squared. Okay. So this is the final form of the function, of the wave function. Okay, we finally got something that we can work with specifically in problems. So everything is uh, we don't work with just conditions and just functions that we don't know what they're about. Okay. Any questions so far? Anything that needs to be cleared? Okay. I'm glad everything makes sense. And now, finally, we will use this wave function to find stuff about the wave function. Okay, so at the fourth point and the last one, D, it says at t is equal to 0, the velocity is a downward parabola in x, maximized at the midpoint x is equal to a over 2 with peak value v0 over 4. So that means that y of 0 at a over 2 is maximum at, no, it's maximum at a over 2 with the value v0 over 4. Okay, differentiating the solution obtained in the point C with respect to time and setting x equal to a over 2, we get function. Let's compute it. So y is let's actually just yeah, okay. Okay, great. Okay, we have the form of x and we should differentiate it. So y derived by t of tx, it will be x v0 over a minus v0 x squared over a squared minus v0 cubed t squared over a squared. Okay, and in setting x is being equal to a over 2, we get okay, good. We get this function in terms of time, and we can further uh, compact this in v0 over 4 multiplied by 1 minus 2 v0 t over a squared. Okay, good. We should show that the time this function vanishes at 2 v0 t over a is equal to 1, which it's clear here. Wait. Oh, okay. Okay. So this function right here vanishes when 2 V0 t over a is equal to 1. That means the maximum velocity comes when t is equal to a over 2 v0. Okay, so when the velocity will be 0, we will get the maximum displacement. Okay, so after finding the time where the maximal displacement occurs, we just replace it in the initial function uh, with the value of x where the maximum takes place, and we get the value of the maximum amplitude of the wave. So doing this, we get y of a over 2v0 and a over 2. Setting it into the function, we get a v0 a over 2 v0 a 2, which is just squared and 4, okay, minus v0 a cubed over 2v0 times a squared times v0 squared, so it's the third power here. Um, no, sorry. It's just v0 here. Okay. Okay, and minus a to the third power over 24a to the third power to the squared, okay, which will get just a here and this is here. Okay, so we get a over 4 minus a over I oh sorry, I'm making a lot of mistakes. Okay, a over 8 minus a over 24. Okay, so computing this here, we get 6a minus 3a minus a over 24, which will be 2a over 24, which will be a over 12. Okay, so we finally arrived to the maximum amplitude of the wave on the string. So by starting with something very general of the general wave function and the general solution of the wave equation, um, we imposed some boundary conditions and also some initial values. And from that, we were able to construct something that is observable. We can test if what is the maximum amplitude and how everything works. So it's quite nice to see how everything comes um, wraps up in such a nice result from something that doesn't say much, from adding tiny bits of information so it describes perfectly by just using the boundary conditions and the initial ones. With so much, so little information, we get so much out of it. Okay, so are there any questions about the result? Again, I'm very sorry for the um, mistakes along the way. I'm a bit tired, to be honest. I promise the PDF will not contain any mistakes. It will be okay there. Okay,
Don't worry, Adrian. It's okay. You did well, so don't worry. It's fine. You did a nice presentation.
okay, I'm glad. Okay, so if there are not any questions, I'm happy to see you all next time, and I hope you had a nice day with us today.
Oh, okay. Thank you very much, everybody, for showing up. I'll stop the recording now. Just a second.